Let's begin with the lecture. So on Monday, we introduced a notion for some sectorial operator L, namely the boundedness of the H-infinity calculus, which means that if we plug L into some bounded function f, then this property means that this always gives some bounded operator f of L, and that we can control the operator norm of f of L by some constant times the supremum norm of f on some angle, on some sector S with angle phi. All right, and yes? Okay, so let's start again. So we introduce the notion of a boundedness of the bounded H-infinity calculus. And we proved some theoretic basics, let's say. And the first was a certain convergence lemma. This was lemma 7.4. And this said that if we have a sequence fj of bounded holomorphic functions on some sector S phi, and if fj itself is bounded and converges uniformly on compact subsets or to some limit function f, then we can say something about the convergence of the operators fj of L applied to some u to f of L applied to u. And the convergence here we proved was for u in the domain of L intersected with the range of L. And as an assumption, we needed that L is an injective sectorial operator. And this was also important in order to define just f of L for bounded holomorphic functions, because otherwise we cannot use this regularizer, which was given by z over z plus 1 plus z squared. Okay, and then we did some, or I showed you some examples, and now I would like to continue with the most important example here for this lecture, which is section 7.3 about the H-infinity calculus of emigrative operators. Okay. Just as a short reminder, recall that we said that an operator L is emigrative if the left complex half plane is contained in the resolvent set of the operator, and if we then can bound the operator lambda plus L inverse in the operator norm by 1 over the real part of lambda for lambda, or for all complex numbers lambda which have a positive real part. All right, and this was the definition of emigrative from the second lecture, or from the second week. And in particular, if you can control this operator norm for all lambda in the right half plane, if you stay away a little bit from the imaginary axis, you can turn by just basic trigonometry, you can turn this real part of lambda into the modulus of lambda, and this means that in particular L is sectorial of angle pi over 2. All right. And there's a certain characterization of M-accretivity, which is as follows, and this is left for you as exercise 7.1. Namely, let's say L is a linear operator, then the following are equivalent. The first condition is that L is M-accretive, which means that we can prove this resolvent bound here with constant C equal to 1 on the right-hand side. And the second property is an application is much more, it's usually much easier to establish in this situation. Namely, the M-accretivity is equivalent to the fact that the real part of the inner product of LU with U is always non-negative for all elements U in the domain of L. And to the fact that there exists some constant lambda greater 0 such that the range of the operator lambda plus L is dense in the Hilbert space H. All right, and these two properties here, they are equivalent. And you will see in the exercises coming from here to here, so from the M-accretivity to this condition, you will get the range condition just from the fact that you have some non-empty resolvent set here, and for the other condition you will just calculate a little bit, and then you will see it, and to get from B to A, you could get some further guidance, let's say, from section 2. Essentially, we performed the proof there already once, but you have to find it. All right, and this range condition here in the second part of the lemma, this is essentially void if L is a bounded M-accretive operator, because if the operator is bounded, then we have only a compact spectrum, and this means that if we take lambda large enough, we end up in the resolvent set, and then this range condition is automatically fulfilled. All right, so the range condition in part B is not needed if L is a bounded operator. All right. Okay, and as I said, the proof of this lemma is left for you as exercise 7.1. Okay, and then we come to the main result that we want to prove today. This is Theorem 7.12. And this is called von Neumann's inequality. This is Theorem 7.12. So let's say, let L be an M-accretive operator, and then we know that an M-accretive operator is sectorial of angle pi over 2, as I said at the beginning. So this means that we can plug L into some holomorphic functions which are defined on a sector of angle strictly larger than pi over 2, right? So let's take some angle phi, which is in the open interval between pi over 2 and pi. And then we have that that the operator norm of f of L in the operator norm of the Hilbert space can be controlled by the supremum norm of f on the sector of angle pi over 2. All right, and here again we have a constant 1 here, so this estimate here is uniform among the whole class of emigrative operators. But I still have to tell you for which class of functions we can prove this inequality, and this is for all functions f in the Dunford-Rees class, E of S phi. All right, and in the following, I will always denote this inequality here by star. Now, I didn't assume that L is an injective operator. If L is an injective operator, then this inequality holds in particularly true for all H0 infinity functions. And then by corollary 7.5 from the last time, we can also extend this inequality here to the whole class of bounded holomorphic functions. And this means that an injective emigrative operator always has a bounded H infinity calculus of any angle phi larger than pi over 2. All right, so if L is additionally injective, then this inequality star is valid for all H infinity functions f so it holds for all f in H infinity on the sector of angle S phi, and in particular L has a bounded H infinity calculus of angle phi. Okay, and always this constant here is just 1 in this estimate. All right, and this will be the theorem. This will be our main theorem here from this lecture today. And essentially, we will deal with the proof of this theorem for the rest now of today. All right. There's the first There's the first remark, namely for Neumann's inequality, it holds true for emigrative operators, but actually for Neumann's inequality is also necessary for a sectorial operator of angle pi over 2 to be emigrative. This is the first remark here. So first remark is that assume that L is sectorial of angle pi over 2, and then let's say we choose, so we in particular know that in the Dunford-Rees class E of S phi, we have resolvents are contained in this Dunford-Rees class, as you might know from chapter 5. And And then we can, in particular, insert L into the function 1 over lambda plus z. And you can calculate the supremum norm on the right half plane of this function, and this is exactly 1 over the real part of lambda. So you see that if we would assume that this inequality, which is denoted by the red star, is valid for this operator, then we can plug the operator into the function 1 over L plus z, 1 over lambda plus z, and then we see that in particular L has to be amacrative. Okay, so choosing F as 1 over lambda plus z for some complex number with a real part strictly positive, and we choose this in von Neumann's inequality star, one sees that that this inequality is also necessary for L to be amacrative. All right. Okay, so now we want to turn to the proof of von Neumann's inequality for amacrative operators. And the idea is somehow to replace L first by some approximation. And we call this approximation throughout the whole lecture by L epsilon. And this L epsilon is defined as follows. We define it here in Lemma 7.13. Namely, for L amacrative and epsilon between 0 and 1, we define the operator L epsilon as what? So we have here our operator L that we want to approximate, and we add some constant epsilon here. But then this L epsilon is not going to be a bounded operator because we just shifted our general amacrative operator, which could also be unbounded. But for epsilon small, the operator 1 plus epsilon L inverse is something like an approximation of the identity, and this is somehow a regularization, let's say, of the operator L. Okay, and we shifted this operator a little bit to the right, so that the operator L, no matter whether it's injective or not, is shifted to the right a little bit, and then the operator L epsilon is going to be an invertible bounded operator, as we will see in the following statements. All right, so the first statement here about this operator is that L epsilon is indeed bounded, and L epsilon minus epsilon is amacrative. In particular, that L epsilon minus epsilon is amacrative is even a stronger condition for L epsilon to be amacrative. So in particular, L epsilon is amacrative. The second statement here is that that this L epsilon operator is not just amacrative, but it's also sectorial of some angle strictly less than pi over 2. Right? Amacrativity means it's sectorial, or in particular means that it's sectorial of angle pi over 2. But we will see that the angle of sectoriality of L epsilon is even stricter less than pi over 2. All right, so these are properties we will need in the proof of von Neumann's inequality. And then we want to perform certain approximation arguments. And if you think about the functional calculus, for example, about the Dunford-Rees class, there are functions like resolvents contained in this class, and in particular, we would like that resolvents of L epsilon approximate resolvents of L. And this is a statement C here. So for all complex numbers C with negative real part, and for all Hilbert space elements U, we have that the resolvent of L epsilon evaluated at Z applied to U converges as epsilon goes to 0 to the resolvent of L in Z applied to U. Okay, so we have a strong approximation property here of the resolvents of L epsilon to the resolvent of L. Okay, and the fourth property we will prove, this is also the last property here of this lemma, is that we can't just approximate resolvents of L by resolvents of L epsilon, but that we can approximate each element in the Dunford-Rees class also by elements, or when I plug in L epsilon into each element of the Dunford-Rees class, we can approximate the corresponding operator when we plug in L into this Dunford-Rees class function. So let's say we take some angle phi between pi over 2 and pi, and then for all elements f in the Dunford-Rees class E of S phi, and for all U in our Hilbert space, we find that f of L epsilon strongly approximates as epsilon goes to 0 the operator f of L. All right, and this will be in the end of the proof. So the strategy of the proof of von Neumann's inequality will be to establish von Neumann's inequality for the operator L epsilon, and then in the end we go over by taking the limit here. Okay, so let's start with the first statement. A. So the first statement was that L epsilon is a bounded operator, and that L epsilon minus epsilon is emocrative, in particular that L epsilon is emocrative. So let's start to prove it, and we start with a boundedness statement. So for the boundedness, we just, the boundedness you can see essentially by functional analysis, by the functional analysis we did in chapter 1. Namely, we have we apply a closed operator to a bounded operator, and the bounded operator maps into the domain of L, and then by the closed graph theorem, it's bounded essentially. But you can also calculate it as follows, and we will need this calculation then for the emocrativity statement, so I will do it anyways. So we start with L epsilon, and this L epsilon was first given by L plus epsilon in the first bracket, and we add and subtract here some number epsilon to the -1, and apply this to the operator 1 plus epsilon L to the -1. And we also take out the epsilon in front of the L. We take it out of the resolvent. So this is the same as epsilon to the -1 multiplied with epsilon to the -1 plus L inverse. Okay, what do we see now here? We have now here a resolvent which is given as epsilon to the -1 plus L, and here we also have the operator epsilon to the minus 1 plus L. And if we multiply them, we get some identity operator. So we just do it. And then we see that, that if we multiply this term by this term, this gives the identity multiplied by epsilon to the minus 1. And then we have to multiply this, this scalar here to this operator. And we also multiply it here by epsilon to the minus 1. And this gives a minus epsilon to the minus 2 minus epsilon times epsilon to the minus 1 plus L inverse. Okay, and now you see we reformulated the operator L epsilon into the difference of some bounded operator here, which is epsilon to the minus 1 times the identity multiplied, and we subtract some operator. Sorry, here should be a 1. We subtract some other bounded operator. So this is in the end a bounded operator on H. Okay, and now we will use this this identity here to prove the M accretivity. Okay. So let's consider the M accretivity of L epsilon minus epsilon. So by the first lemma which I wrote on the blackboard today, the exercise that you have is that M accretivity can be equivalently formulated by a condition on the real part of the inner product of LU with U, right? Or L epsilon of U with U. And L epsilon is a bounded operator, as we just saw, so we only need to verify this condition, and the range condition, which was also stated in this lemma, is not needed, as I wrote it below. So let's consider for the M accretivity the real part of L epsilon U with U. Okay. And now we use this identity above there, so we replace L epsilon by the right-hand side of this inequality there, and we get that this is the same as as epsilon to the minus 1 times the norm of U squared minus epsilon to the minus 2 minus 1 times the real part of the inner product of the resolvent epsilon to the minus 1 plus L inverse applied to U, and this is tested by U again. Okay. And now in order to prove M accretivity, we would like to derive a bound from below of this expression, and we would like to show that this is that this here is a positive quantity. But we also want to prove M accretivity for L epsilon minus epsilon, so we need some proper bound from below by epsilon times the L2 norm of U squared, essentially. And we have here already some L2 norm of U squared, and here we have this inner product, and we can estimate this whole term here from below by making this expression here larger. So we can estimate the real part, or we make the real part of this inner product always larger if we apply, for example, Cauchy-Schwarz inequality to this inner product, and then we apply here the resolvent, just the definition of the operator norm, and this can then be controlled by the operator norm of epsilon to the minus 1 plus L inverse times the norm of U squared. Okay. And now, by assumption, L is an M accretive operator, which means that I can control this operator norm here by 1 over this number. And 1 over epsilon to the minus 1 is just epsilon. Okay, so I can control this here again from above by epsilon, essentially. So this means that this whole expression here is bounded from below by epsilon to the minus 1 times the Hilbert space norm of u squared minus, and now I can replace this here by epsilon, and I multiply this here by this parenthesis here. So we have here some epsilon to the minus 1 minus epsilon, and then I'm left with the norm of u squared. Okay, and now we see that these two terms here just cancel out, and we remain with epsilon times the times the norm of u squared. Okay. Now remember, the norm of u squared is just the inner product of u with u, and if we subtract this here to the left-hand side, we would see that here the operator L epsilon u minus epsilon times u would be given if we subtract this term here to the left-hand side, and this would still be non-negative, and this means that that L epsilon minus epsilon is emigrative. This is by Lemma 711. Okay, and in particular, in particular, we see here already that if this here, so because we can bound this here from below by some positive quantity, in particular, it's also non-negative, and this also means that L epsilon is also emigrative. All right. So this was the proof of part A. Let's consider part B. What is part B? It means that the angle of sectoriality of our operator L epsilon is even strictly less than pi over 2. Right? We know now it's emigrative, so it's sectorial of angle pi over 2, but it's even better. So let's say we prove now part B. So what do we know? We know L epsilon is bounded, and we know that L epsilon minus epsilon is accretive, is emigrative by the thing we just proved. So what does it mean? It means first that the boundedness of L epsilon implies that the spectrum of L epsilon is compact, and because L epsilon minus epsilon is emigrative, we know that the spectrum of L epsilon minus epsilon must be contained in the right half plane. But now this is just the operator L epsilon, which is shifted by epsilon. So if I shift some operator by epsilon, and if the spectrum of the shifted operator is contained in the right half plane, this means that the spectrum of L epsilon itself is contained in the plane which starts at real part epsilon. So the spectrum of L epsilon is contained in the part of the complex plane of all complex numbers which have a real part larger than epsilon, greater or equal than epsilon. So, okay. And if we paint a picture here, we thus know that the spectrum is compact and it's here to the right of epsilon. So let's say epsilon is maybe here. So the spectrum would be somewhere here. Okay? And if the spectrum is here on the right hand, it has a positive distance to the origin and it's on the right hand side, then I can also find a sector which contains the spectrum here. And the sector has some angle nu, and this angle nu is strictly less than pi over 2. So there exists some angle nu strictly between 0 and pi over 2, such that the spectrum of L epsilon is contained in the closure of this sector of angle nu. So we know already where the resolvent set is, essentially from our operator L epsilon. And now the question about the sectoriality is a question about the resolvent estimate outside of the sector, essentially. So let psi be some angle between nu and pi. And let's say we take R epsilon to the operator norm of L epsilon. And we know that that the resolvent function R, the resolvent function of L epsilon, is continuous. In particular, now it was holomorphic, and in particular it's continuous. So this means that if I stay somehow in the neighborhood of the origin in this picture there, then this continuous function stays bounded, right? Or the norm of it is also a continuous function, and this continuous function stays bounded. So it means there exists some non-negative constant c, such that for all resolvent parameters z, which are not contained in the sector of angle psi, which is slightly larger as the sector with angle nu, and let's say we take resolvent parameters which stay bounded, so which are, for example, in modulus less than 2 times this constant R epsilon, we have that this continuous function simply stays bounded, right? It's a continuous function on a compact set, so it is bounded. And then, in particular, this means that this resolvent can be estimated by a constant over z, right? Because z would explode for small z, and then I can control this resolvent here by a constant over z. Okay, and then we only have to consider the case where z is large, so larger, let's say, than 2 times this constant R epsilon, and then we need to control the resolvent there. And this is something we can't do by continuity or something. But the way out is to use a Neumann series argument. So let's say we take the resolvent of L epsilon in the operator norm. Then I take out the z here, and this is then the same as z inverse times 1 minus z inverse multiplied by the operator L epsilon, and then we take the inverse here. Okay, now I have here the inverse operator of identity minus some bounded operator, and this bounded operator here has operator norm less or equal than 2, right? Because z is, or the modulus of z is larger than 2 times the operator norm of L epsilon. So in particular, this means that the operator norm of this operator is less or equal than 1/2. And if I take the identity minus some small bounded operator, I can compute this inverse operator by a Neumann series. And this means that this is the same as the operator norm of its Neumann series. So I multiply again the inverse of z by the Neumann series. So I sum from k to equal to 0 to infinity, and I have to multiply I have to sum over z inverse times L epsilon to the k, and take the operator norm of this. Okay, and then I pull in I use a triangle inequality, and I can estimate each of these operator norms here by 1/2, and this gives me a geometric series, which means that altogether this is less or equal than 2 over the modulus of z. Okay, and this means that, and this is exactly the resolvent estimate. And there you see we didn't really use the fact that L epsilon is amocrative or something. We just used the fact that the spectrum lies in a appropriate sector, essentially. We just use the amocrativity to show that the spectrum lies somehow on a sector of angle strictly less than pi over 2. Okay, so now we proved part B, and now we go over to C. So we want to see now that the resolvents of L epsilon are a strong approximation of the resolvent of L. So let's go over to part C. Okay, we will take V to be the resolvent of L in Z applied to this function U, and this, because this is the image of of a resolvent mapping, V is contained in the domain of the operator L. And then we write the expression that we want to control, so the difference of the two resolvents. We write it as follows. We take first the resolvent of L, apply it to U, and then we take the resolvent of L epsilon and apply this to U as well. Okay, and now this is the argument which is performed quite oftenly, that if you take the difference of two resolvents, you can pull somehow the resolvents out, and I will take out this here to the left and the resolvent here to the right. So this is the same as the resolvent of L epsilon multiplied by something. And on the right-hand side, we also take out the resolvent of L and apply this to U. Okay, and if I take out the resolvent of L epsilon to the left, we are left here with Z minus L epsilon, and I take out this here to the right, so we end up here with minus Z minus L. Okay, and you see that the two Z's here, they just cancel, and we get here L minus L epsilon. And furthermore, we defined V to be exactly this here on the right-hand side. So this here is just given by the vector V. Okay, so this is the same as the resolvent of L minus epsilon of L epsilon multiplied by L minus L epsilon applied to V. Okay, and L minus L epsilon is given by definition as L minus, and now I just plug in the definition of L epsilon, which I erased already, but you can believe me, it's just the definition. All right, so the left-hand side is exactly here, this right-hand side. Okay, and the last thing we do is essentially just multiplying here epsilon by this resolvent and L by this resolvent. And then we are going to investigate what's happening there. Okay, now I can erase the rest of the blackboard. I think you believe me that we still prove this property here, which I erase now, so that the resolvents of L epsilon approximate strongly the resolvents of L. So I continue this chain of equations here, and see that this is the same as the resolvent of L epsilon multiplied by LV minus, now I shuffle the expressions, minus L times the resolvent of 1 plus epsilon L applied to V minus epsilon times 1 plus epsilon L inverse applied to V. Okay. And now we want to start to estimate this term. Okay, we want to prove that the resolvents of L epsilon strongly approximate the resolvent of L. So this means that the left-hand side here shall become small if epsilon tends to 0, right? But the problem is we have here a resolvent of the operator L epsilon, and we need to estimate it. And here is really a crucial property that we have now, is that L epsilon itself is an ammocrative operator. So we have here a resolvent bound which is given with constant 1. Okay, and if the constant is 1, it doesn't depend on epsilon. So it's uniform with respect to epsilon, and then we can conclude. So this is really here a crucial point, that L epsilon is ammocrative. And this implies a resolvent bound independent of epsilon. Okay. So we see that if we take now norms here of our chain of equalities, that that the norm of the resolvent of L applied to U compared with the resolvent of L epsilon applied to U can be controlled by 1 over the absolute value of the real part of Z. Now recall, Z is now a complex number which has negative real part in this calculation here. And then we apply the triangle inequality here for this remaining part, and we will compare these two terms here, and this here will be left alone, essentially. Okay, so I take the Hilbert space norm of this expression, so this is LV minus, and now I compute the operator L with its resolvent. So this gives the resolvent applied to LV minus epsilon times the resolvent of 1 plus epsilon L inverse applied to V. Okay. Now, the easy thing here is this term here just stays bounded by resolvent estimates. All right, this here is just, so without this epsilon here, this is just bounded by 1 times the norm of V. Okay, so independently of epsilon, and I multiply it by epsilon, so it tends to 0 for epsilon to 0. Okay, and here we proved already in proposition 2.4 that that for epsilon to 0, this is a strong approximation of the identity. Yeah, this is what we proved. So if we send here epsilon to 0, it tends to LV. So in particular, this whole expression here tends to 0 for epsilon to 0 by proposition 2.4. Okay. And this is a proof of C. So altogether, this converges to 0 as epsilon tends to 0. Okay. And now we proved that the resolvents of L epsilon strongly approximate the resolvents of L, and it remains to prove the statement D in the left upper corner there, namely that that for all functions in the Dunford-Rees class, even we have a strong approximation of the operators f of L epsilon to the operators of f of L. All right, so let's see why statement D is true. And then we have proven this lemma here. So we write, so because f is from the Dunford-Rees class, it's a sum essentially of three possible elements. So f could be a sum of some constant functions. It could be this. I could also sum resolvents of L, and I could take this, or in the sum could appear H0 infinity functions. All right, and essentially there's nothing to do if f is just the constant one function, right? And this also then takes over to any constant function. If f is just a constant one function, then f of L epsilon is just the identity, and f of L is also the identity, so clearly they approximate each other strongly, right? They are equal. And for resolvents, so in particular the function f being given by 1 plus z inverse was one of the functions which generates the algebra of the Dunford-Rees class. And this is a resolvent of L. So the strong approximation property here follows just from the part we've just proven. Okay. So and then it remains to prove the statement for H0 infinity functions. So let's say f would be a function in H0 infinity on the sector of angle phi. Then write, and we do this here by fixing an integration angle psi between pi over 2 and phi. And and then we just use the definition of the functional calculus for H0 infinity functions. So we plug L into the function f, and we compare it to L epsilon plugged into the function f, and we apply it to U. Okay, by the very definition of the functional calculus, both of these terms are given by a Cauchy integral formula. And in this Cauchy integral formula, the main player is a resolvent, but the resolvent is something we have already under control from part C. So let's write this here via the Cauchy integral formula. So this coincides with 1 over 2 pi I multiplied by the path integral over the path gamma psi, and we integrate over f of z times the resolvent of L applied to U minus the resolvent of L epsilon applied to U. Okay. And now the good thing here is again L epsilon is amocrative, and we chose our angle here is strictly larger than pi over 2, so the path it runs through the left complex half plane. So this means that we can control the resolvent here again by the constant 1 times the real part of z. But as the z comes even from a sector with a strictly larger angle, we can again replace the modulus of the real part by the modulus of z. So altogether, the resolvent part here is controlled by part C, or let's say by the steps we've done in part C, by a constant C over the modulus of z times U in times U in the Hilbert space norm. I don't know what did I wanted to say. This is part B here. This is the sectoriality of L epsilon and the amocrativity. So even we have here part A. All right. And So we multiply here by some constant independently of epsilon, and we divide by the modulus of z, but also the function f here is from h0 infinity, so it gives you some additional decay in 0 and at infinity, which makes this whole integrand here integrable uniformly with respect to epsilon. Okay, and this gives us an integrable maturant for this integrand here. And part C tells us that the integrand also converges to 0 for epsilon to 0. So the dominated convergence theorem applies and tells us that if we send epsilon to 0, the right-hand side tends to 0. And this is what we wanted to prove. So this here converges to 0 as epsilon tends to 0. So right here, this tends to 0 by C. And the argument is the dominated convergence theorem. Okay, so now we have seen all properties we need in order to prove von Neumann's inequality for the operators L epsilon. I would say that we take a break now and then go over into the proof. Good. So let's turn to the proof of von Neumann's inequality. So we turn to the proof of theorem 7.12. And as I said already at the beginning, we are going to prove von Neumann's inequality first for the operator L epsilon. So we prove this inequality red star in the theorem for L epsilon. Okay, and we fix some function f, which is first just h0 infinity. Okay, because the advantage is again that we can calculate f of L or f of L epsilon again by the Cauchy integral formula, and this angle phi was some angle which is strictly strictly larger than pi over 2. Oops. So phi would be here on the left. So this would be a sector here on the left-hand side. Okay, I painted here again the picture which we had on the blackboard earlier with the spectrum of L epsilon here in a sector on the right-hand side. The phi is some angle which is here, which is quite large, and in particular f is holomorphic here on this big sector. Okay. So we prove we use the lemma which we just proved, part A and B, to conclude the following. Namely, that the function which maps z to z plus the adjoint of L epsilon inverse, that this is somehow holomorphic on a right half plane which starts a little bit to the left of the origin. Namely, if you have L epsilon, or the spectrum of L epsilon here on the right hand side, if we take the adjoint operator of L epsilon, we have to take the complex conjugates here of the spectrum, so it stays again here somehow in this neighborhood, or it remains still in the same sector, let's say. And then we consider we don't have here a minus but a plus, so it means that actually we consider the resolvent of minus L epsilon star, which means that if we consider minus L epsilon star, we would also reflect the whole spectrum here to the left-hand side. And it means on the right-hand side, let's say for the spectrum would lie to the left of minus epsilon. Okay, and this is something we use now. So this is holomorphic. This function here is holomorphic on the set of all complex numbers z with the property that the real part of z is strictly larger, is greater or equal than, strictly larger than minus epsilon. And we also have a resolvent bound of the form z plus L epsilon star inverse in the operator norm is controlled by, let's say, a constant times z to the minus 1. Okay, we even have a better bound because here this inequality would suggest that we somehow blow up at the origin, but we don't do it because it's holomorphic around the origin. But we, in particular, have a bound of this form here, which means that we have some decay at infinity. And the holomorphy means that around the origin we also don't blow up. Okay, so the only critical point is somehow around the origin. And now we use Cauchy's integral formula for a certain calculation. Namely, Cauchy's integral formula tells us that if we integrate over the holomorphic function f of z times z plus L squared L epsilon star inverse over dz, and if we integrate now on a path with angle pi over 2. So this will be our path over which we are going to integrate now. And this is one particular fact why we introduced the approximation L epsilon in order to choose this path here. This is really one crucial situation. So this is a path gamma pi over 2. Okay, so this function which we integrate there is holomorphic in a neighborhood of this path, and we have a control on the resolvent and additional decay of the function f, which means that we can indeed use Cauchy's integral formula and see that the integral over this holomorphic function just vanishes. Okay, and now we start to calculate. And now begins somehow the magic of everything. So we plug L epsilon into the function f, and then by definition, this is 1 over 2 pi I times the integral over the path with angle pi over 2, and we integrate over f of z times the resolvent of z minus L epsilon. This is just the definition of the operator f of L epsilon. Now we use this property here. Sorry, I forgot to write the path of integration. So we integrate here also over the path gamma pi over 2. And we use this fact that this vanishes, so we can subtract this term here in the definition of f of L epsilon just for free. Okay, so this coincides with 1 over 2 pi I times the integral over gamma pi over 2 times f of z times, now we have the resolvent of z minus L epsilon minus z plus L epsilon star inverse dz. Okay, so this is just the formula we had before. And now we do the same trick as before. We take out the operator here to the left-hand side and the other to the right-hand side. And so this coincides with 1 over 2 pi I times the integral over the path gamma pi over 2 times f of z times the resolvent z plus L epsilon star times, we get here some L epsilon star, and then we have here a minus and a minus, so we get a plus L epsilon And we took out also the resolvent here to the right-hand side. So this is, we have here z minus L epsilon inverse dz. Okay. So this was already some magic. We have now a new formula somehow for f of L epsilon. And now we want to know the norm of this operator. So we start to test this operator by elements u and v in the Hilbert space H, and we get that the inner product of f of L epsilon applied to u and tested with v, this coincides with 1 over 2 pi I times the path integral over the path gamma pi over 2. And then because the inner product is a continuous operator, we can pull it into the integral and take out f of z, for example, because it's just a scalar. And we have here the inner product of this operator here applied to u, and we multiply it by v. Okay, and then if we have an inner product, we can use the definition of an adjoint operator and move this operator here to the right-hand side. So we apply this here to the function v. So we get here L epsilon star plus L epsilon multiplied by the resolvent of L epsilon. This is applied to u, and here we also use the definition of the adjoint operator. So we get here the resolvent evaluated at the complex conjugate z bar plus L epsilon inverse applied to v. Okay, so this is one important formula here, and now we use some other important fact that one important property that comes from the fact that we can integrate here, because the L epsilons are sectorial of angles strictly less than pi over 2. We could integrate over this path here, and this path has the unique property that the complex conjugate of z is just the same as minus z. Okay, because we are on the imaginary axis. And we use this property here, namely we replace now the complex conjugate of z by minus z, and then take out the minus sign. So we get a minus sign in front of the integral. But the path also comes from plus infinity and goes to minus infinity. So if I plug in the parametrization of the path, I get an additional minus sign. So this quantity there, it coincides with I don't take in the parameterization of the path yet. So this coincides with minus 1 over 2 pi I. We integrate over gamma pi over 2 over the function f of z times the inner product of L epsilon star plus L epsilon times z minus L epsilon, or the resolvent of L epsilon. Apply this to u, and then because we took out the minus 1 here, we test again with the resolvent of L epsilon applied to v and integrate with respect to dz. Okay, and so this whole equation here will be denoted, let's say, by the red triangle. And here we have some operator, and this operator here will be denoted by t. Okay, and this operator t is the sum of two bounded operators. So in particular, it's a bounded operator. Now, we also have here a symmetry property, namely here this is a self-adjoint operator, because we just take the sum of the operator and its adjoint, and then this gives you a self-adjoint operator. So first property is that T is self-adjoint, and T is also M-accretive, because we can calculate the real part of the inner product of Tu with U, and remember, for bounded operators, the non-negativity here of this property is equivalent to the M-accretivity by the first lemma here of this lecture today. And we plug in the definition, T is equal to L epsilon star plus L epsilon. So this coincides with the real part of the inner product of L epsilon U with U plus the inner product of U with L epsilon U. Okay, but this itself is again the real part of the inner product of L epsilon U with U, or twice this real part. And by M-accretivity of L epsilon, this is non-negative. Okay, so T itself is not just a self-adjoint operator, it's an M-accretive operator. And so by lemma 7.11, it follows T is M-accretive. And thus it's also sectorial of angle pi over 2. And for a sectorial operator, we can define the square root. And from corollary 6.11, we know that the square root of a self-adjoint sectorial operator is again a self-adjoint operator. So this is self-adjoint. And by exercise 6.1, we find that the square root is also bounded, because T is a bounded operator. Okay. And this step here is crucial, or this step here as well is crucial for the whole proof. You can even for real numbers, you can define square roots which are not self-adjoint if you view them as a multiplication operator. For example, if you multiply U by -1, then the square root would be something like the multiplication by the number I, but multiplication by the number I or by the imaginary number is not self-adjoint. Okay, so here was a crucial property that L epsilon is indeed M-accretive, and this comes from the M-accretivity of the operator L. So this is a key step here in the proof. Okay. So we use now our equation star, which is up there in the left upper corner and in the right lower corner. It starts in the right lower corner and ends in the left upper corner. We use this equation, and then we plug in the parametrization of the path gamma. Gamma pi over 2, and we find now a new identity, namely that f applied to, or L epsilon plugged into f applied to u and tested by v, that this is the same as 1 over 2 pi times the integral from from minus infinity to plus infinity. And now we integrate over f of it. So the path gamma pi over 2 was essentially parameterized by I times t. And because t is self-adjoint, or the square root of t is self-adjoint, we split up t into two square roots and distribute them equally into the inner product. And we have here the inner product of the square root of t multiplied by the resolvent evaluated in I times t. And we tested, we multiply this again by the square root of t times the resolvent of IT minus L epsilon inverse V dt. Okay. And this is some identity, a new identity, which we denote now by square. And I claim now that this identity doesn't just hold for H0 infinity functions, but for all H infinity functions. So for all bounded holomorphic functions, should this equality hold. So claim this equality square, it holds for all bounded holomorphic functions on the sector S phi. So let's prove this claim. So heuristically, this holds because by our trick, by introducing this new integration over the resolvent of this adjoint operator, we gained now some additional decay here in this integral. Namely here, the resolvents of L epsilon, they don't explode in zero because, as you see on the picture, the resolvent stays away, or the spectrum stays away from the origin or from the imaginary axis. So there, the resolvent doesn't explode here in the neighborhood of the origin. And for large t, we have here some decay of 1 over t due to the sectoriality, and here another decay of 1 over t. So altogether, at infinity, we decay like 1 over t squared. And this means that even for bounded holomorphic functions, this formula here makes sense because we gain integrability just by this inner product here. Okay. And this is done by the convergence lemma, the proof that we can indeed plug here H infinity functions inside. So let f be an H infinity function on S phi and take a sequence of bounded holomorphic functions which is bounded with a property that fj converges to f for j to infinity uniformly on compact subsets. All right. So, and by lemma 713, we know that L epsilon is invertible. So indeed, the resolvents don't blow up at the origin. And in particular, because it's invertible, it's also injective. Furthermore, it's a bounded operator. So the domain of L epsilon is the whole Hilbert space. And because it's invertible, its range is also the whole Hilbert space. So the range of L epsilon coincides with H. Now the convergence lemma tells us that that we have strong convergence of f of L epsilon on the intersection of the set. This is what we proved on Monday. But the intersection of the set is just the Hilbert space. It's just all of H. So so f of L epsilon approximates fj of L epsilon approximates f of L epsilon strongly on the whole Hilbert space by the convergence lemma. So the convergence lemma tells us that if I consider fj of L epsilon, apply it to U and test it with V, that this here converges for j to infinity to f of L u tested with V. I'm sorry, I did one mistake. I wanted to take fj as H0 infinity functions. This is something we also did on Monday, that we multiplied bounded holomorphic function by functions of the form z to the 1 plus z squared, and then we took the jth root. So if we consider this function here, this is a sequence of functions which approximates f uniformly on compact subsets, and each of these functions, they are even contained in H0 infinity. Okay. So, and on H0 infinity, we have our identity square. All right? And now we apply these fj's of L epsilon to any Hilbert space element, and we see that these inner products here, they converge as well by the convergence lemma. So for the right-hand side, so this is already the convergence of the left-hand side of this identity here, and we only need to verify that the right-hand side converges as well. But for the right-hand side of this identity, if I plug in fj instead of f into this identity, then we notice that the integrand is controlled by this. Sorry, I just copied the integrand here. We have the inner product of the square root of t times the resolvent u. So this inner product here, this is controlled by, let's say, a constant over t squared, let's say +1, because we don't explode in 0. Okay, and then we have here also the norms of u and v. So we can control this here by some convergent or by some integrable function, and then we don't need integrability here of these fj's anymore. And they converge pointwise to f, so we can also take, by the dominated convergence theorem, the limit j to infinity here on the right-hand side. So dominated convergence tells us that we can indeed take also the limit j to infinity on the right-hand side, and this is exactly the claim, namely that that this identity square also holds for all h infinity functions f. All right. So we can take here in the square identity, we can take f now just as the one function and u equal to v, and this gives us a description of the norm of u by means of this integral. So we take f just to be the one function, and u equals v in this identity square, and we see that the norm of u squared is given by 1 over 2 pi times the integral over r over the norm of the square root of t times the resolvent evaluated at it of L epsilon applied to u squared dt. Okay, so this is how we can now express the norm of u for any Hilbert space element u in H. And now we can conclude for Neumann's inequality for the operator L epsilon, namely, if f is now an H infinity function on S phi, then we can use Cauchy-Schwarz inequality as well as our identity square. And this gives us that the modulus of this inner product of f of L epsilon applied to u tested with v And this can be estimated as follows. So we use Cauchy-Schwarz above and so estimate the inner product by the product of the norms of each of these entries, and then also use Cauchy-Schwarz inequality in the integral. So we get something like an integral over R, and we take the norm of the square root of t times the resolvent at it minus L epsilon u squared dt times an integral over R, and we take again the norm of the square root of t times it minus L epsilon inverse v squared dt. Okay, and what I missed now is the 1 over 2 pi and the norm of f. Okay, and because we don't need the decay of f for the integration anymore, we can take it out by the supremum norm. So I add here at the front of everything the supremum norm of f on the angle on the sector with angle pi over 2 and divided by 2 over pi. Okay. And now you see here we have a certain description of the norm of u and of the norm of v by means of these integrals here. And if you look at it, you see that this is equal to the supremum norm of f times the norm of u and the norm of v. Okay. And now you see here that we get a norm bound of the operator norm of f of L epsilon by the L infinity norm of f. So take v to be f of L epsilon u, and then we conclude that that f of L epsilon applied f of L epsilon, the operator norm of f of L epsilon is controlled by 1 times the supremum norm of f on the sector of angle pi over 2 for any f in H0 and H infinity on this larger sector S over S phi. Okay, and this is the claim, this is essentially the von Neumann inequality for the operators L epsilon, and I call this here star epsilon. And the final step is to rescue or to transfer this inequality here by approximation to the operator A. So the final step would be to approximate L by L epsilon. And I just notice here that we've proven in lemma 7.13 that if f is in the Dunford-Rees class, we have the strong approximation property of f of L by operators f of L epsilon. So we see that that f of L applied to u can be written as a limit for epsilon to 0 of f of L epsilon applied to u. Okay, and now each of these terms can be controlled by the supremum norm of f. So this is less than the supremum norm of f on the angle pi on the sector of angle pi over 2 times the norm of u. So this is the inequality for the Dunford-Rees class for any sectorial operator just by approximation. And if now additionally L is injective, we also have corollary 7.5 at hand, which tells us that if we can prove a bound for H0 infinity functions f, which are included in the Dunford-Rees class, then we can transfer it also to all H infinity functions in the case of injective operators. And this is the boundedness of the H infinity calculus for L. And this is essentially it. Okay, so I think I leave it aside, and thank you for your attention, and have fun in the next courses.